Guten Morgen. Wie geht's? That's as far as my German goes. But catch me next week. I'm not quite up to the category of Ich bin ein Berliner. But it'll come. Anyway, I hope you had a good night's sleep and caught some interesting restaurants. And if you find a really good restaurant, tell us about it. We're searching for some. So I think, how many of you are new who weren't here yesterday? I think very few.
Well, actually quite a few.
A handful, okay. All right, welcome. I'm glad you found the place. We wanted to start with asking, how many of you are actually current Mplus users?
Oh, lots.
And how many have never tried Mplus so far at all? Okay, all right. So 2/3, 1/3, or 75%, 25%?
I think 75, 25.
Okay, all right. It's a good sampling. And let's see. We wanted to...
Well, maybe I should just talk about it. So for those, since we have a handful of new people, basically we start at 8:30, we end at 5. We have 4 1.5-hour segments with breaks in between the 2 in the morning and the 2 in the afternoon, and lunch from 12 to 1:30. So we ask that people not ask questions during the segment, but rather to make a note of your question. If it hasn't been answered by the end, then we will take questions toward the end of each 1.5-hour segment and answer as many questions as you have. If we take questions, then it breaks things up, and if each one of you asked one question, we would never finish by 5 o'clock, and we'd have to keep you here till midnight, and I don't think you would like that.
Yeah, we have a lot of topics that we want to cover. So the idea of these 4 days is to give you an overview feel for what you can do these days with modern latent variable techniques and with the Mplus program. So we have chosen deliberately to take that overview tack instead of going in depth on any one specific topic or doing computer exercises, because we want you to give that feel for how much you can do to sort of have that bird's eye view of the area of latent variable modeling. And then you can come back and get more in depth in certain areas. We also want to say that all of what we're talking about really has the very small building blocks of regression analysis. And by that I mean linear regression analysis for continuous dependent variables. And also building block of categorical data analysis, including logistic regression with categorical dependent variables. Those are 2 building blocks that we don't have time to penetrate very much, not even when you go through all of our 8 days. So for those of you who want to do serious analysis using the Mplus program, I would recommend taking at least 2 university courses, 1 good course in regression analysis for the standard case of a continuous dependent variable. So linear regression analysis, a good course on that will serve you well and cover a lot of the issues that come up in our modeling. And the other course you should take is categorical data analysis. Just become familiar with dealing with categorical variables. Not only logistic regression, but you also get to hear about all kinds of probability models and basic knowledge like the multinomial distribution that we only talk about in passing. So don't think that this is sufficient. If you really want to be a serious analyst, it behooves you to dig a little deeper. And then you will feel much more comfortable writing up your results as well. So with that introduction, do we want to say anything else?
Well, just to repeat it again. So basically, Mplus is just, when you run a model in Mplus, you're doing a set of regressions. They could be linear regressions, logistic regressions, probit regressions, but there's nothing magic about the statistical basis of the Mplus program. What's unique is that we put together all of these various types of regressions that can be estimated in a model simultaneously. And we have not only observed variables, but latent variables, continuous latent variables, and categorical latent variables. So all of the issues that are issues in regular regression, like multicollinearity, or Bonferroni corrections of doing multiple tests, or outliers, or any of those. These are also issues for the models estimated in Mplus because they're regression based. So and if you understand that, then by the scale of your dependent variable, you'll know what kind of regression you have in the Mplus output. So if you have a continuous variable, it's a linear regression. If you have a categorical variable, it's either probit or logit, depending on the estimator. Count variable is some type of a logistic regression also, right? And censored is a linear regression. So once you know the type of dependent variable, then the type of regression coefficient is defined by that, and there's nothing different than in the literature on how we estimate these particular regressions. So I think sometimes people think it's something different, but it isn't. It's, you can read the Agresti book, you'll understand exactly what we're doing for categorical outcomes, the Hilba book for count outcomes, etc. So just to make it not seem like it's something different than it is to you.
But there is some magic behind it.
Well, of course.
And the magic is
put together, not
is in putting it together. Yeah, and also the algorithms behind this. You would not want to see the code.
No, I always say to Bengt, if anybody stole our source code, they would be immediately put in a mental hospital if they tried to decipher it, because it's so complicated. We used to try to make our programmer document what he was doing, and then we've just given up because what he does is so complex. Even if he documented, we probably would never understand it anyway. Okay.
So with that, let's get right into the action, and I will not repeat the introductory slides, but we'll start on slide 8. The earlier slides are self-explanatory to a large extent anyway. And as I was explaining yesterday, what we are doing, we are starting midway through an 8-day series of short courses, Mplus short courses, and they follow the format that we teach every year at the Johns Hopkins University in Baltimore, the USA. And we are skipping then topics 1 through 4, the first 4 days, and going straight to topic 5, the 5th day, which was treated yesterday, and today we are at topic 6. And topic 6 is longitudinal modeling and relies quite a lot on topic 3, the introductory and intermediate growth modeling. But in my email I urge you to study these the videos of these first 4 days as an introduction to what we're doing today. But even if you did not have time to do that, you will have a chance. We'll give you some introductory slides corresponding to each new topic to give everybody a chance to get up to speed. So we're going to go right into it, and we're going to talk about more latent variable models. And a very basic latent variable model is one that is, in statistics, it is called a hidden Markov analysis, hidden Markov. I don't know who hidden, but statisticians talk about Markov analysis. We will talk about transition analysis as well. And there are some differences between the two. I'm going to point that out, the connection between the statistical field and the more behavioral methodology field. Well, let me just give you the general feeling for it. In statistics, when you talk about longitudinal data in a Markov setting, you typically work with only one variable at each time point. This, you may write time 1 here, time 1 up here, and time 2 time points. And statisticians typically work with a single measure at each time point, U1 and U2. They, however, typically have very long time series. Here we have only 2 time points. They typically work with maybe 100 time points, such as in speech patterns over time. We are going to talk about the behavioral methodology area of latent transition analysis, where we're going to talk about rather short time periods, like 1, 2, 3, 4 time points maybe. But for each time point, we're going to have multiple indicators. So multiple measures that tries to capture a latent class variable. So there is that distinction or connection between Markov analysis and the transition analysis. Now, if you look at this picture here, it is a picture that has features of what we talked about yesterday. Excuse me. We have, say that we have binary variables to begin with. So we use the generic notation of U, two binary dichotomous variables, and we have a corresponding latent class variable, categorical latent variable C1 that has two categories, and C2 that has two categories. So the relationship between C2 and C1 is written as a regression of C2 on C1. So C1 influences C2, or C1 predicts C2. And one traditional way of describing that relationship is in terms of transition probabilities. So you have the rows being the time point 1 latent class variable with its two categories, and the columns being the time point 2 latent class variable. And the way you read this table is among those who started in class 1, C1 equals 1, 80% stay in that low class at time 2, and 20% move to another class. They transition into another class. So these two probabilities sum to 1. Likewise, if you start in the high class, you have a 60% chance of staying in the high class and 40% chance of moving to the lower class. So you have the stability on the diagonal and the transitions on the off diagonal. People are interested in looking at these transitions between states, between latent classes over time. And you can do it for more categories than 2, and you can do it for more time points than only 2. Now, how you go from the regression to these probabilities is something we're going to talk about a little bit. And much of it is described in Chapter 13 of the User's Guide. And again, the User's Guide is freely available on the website. If you want a hard copy, you can also purchase it. We'll send it to you. Chapter 13 talks about how the regression of C2 on C1 is expressed by a multinomial logistic regression, unordered multinomial logistic regression of C2 on C1. And you recognize the formula from yesterday, the multinomial logistic regression, probability of C2 assuming a certain category, given that we were in a certain category at C1, is expressed as the e to the power of, that is exp, e to the power of something divided by the sum. And the sum is, in this case, over the two C2 categories. So you sum over the columns here. You may not want to penetrate all of the details of this right now, but just to note that C2 influenced by C1 is expressed by multinomial logistic regression. And that Chapter 13 in the User's Guide describe these relationships, and in fact then uses a series of logits. If you look at the bottom left here, you have logit parameters A and B describing the logits for the cells. In this case, it's a 3x3 situation, 3 classes at time point 1, 3 classes at time point 2. And you have A's standing for intercept, B standing for slopes. A is the intercept. If you look at the left screen, A is the intercept for the dependent variable, and B is the slope. So you sort of think linear regression or logistic regression. Intercept and slope, A and B, come into play. And on this slide 12, you also have the relationship between the names A and B and the corresponding Mplus language notation. Intercepts being in brackets. So intercept for C2, first intercept and the second intercept, and the B's being the regression coefficients, which is handled by the on statement, C2 regressed on C1 for each of the different categories. And again, since we do multinomial logistic regression, the last category of the dependent variable has its logits fixed at 0 as a standardization. And that is then a standard feature of the multinomial logistic regression. But ignoring the technical details there for a second, your analysis, when you say C2 on C1 here, it's going to produce in the output a derivation from the estimated A and B parameters. We're going to print a transition probability matrix like this that you can then interpret to see how much class status changes over time. And again, we have then two parts to the model, a structural part describing the distribution of people, structural part, the latent variables describing the people, and measurement parts, one measurement part at time 1 and a second measurement part at time 2, describing features of the variables as a function of the observed variables as a function of the latent variables. Now, what I want to do first here, since we have fresh minds, I'm going to do some technical things here. We're going to focus on the measurement part for a second and just exercise some techniques here. Not too much, but a little bit. We're going to try to bring in the concept of measurement error in the setting of categorical variables. In this case, categorical observed and categorical latent. And by the way, as an aside, the observed and the latent variables do not have to be of the same scale. You can have any combination of those that suits your application. Any combination of scales. So in this case, they just happen to be the same, and they happen to be binary. So let's see, if you have this situation, then this may be time point 1, the time point 1 measurement relationship. What do we mean by a binary indicator U measured without error? Well, let's look at the measurement, and measurement is then described as how the observed relates to the latent. So U given C, or U as a function of C. What's the probability of that? So you have U as columns here, 0 and 1, the low being 0, the high being 1, and the rows being the latent variable, and the low values 1 and 2 by convention. If you have a perfect measurement error-free relationship, then if you are in the lowest latent category, you should have probability 1 of answering in the lowest observed category, and probability of 0 of answering in the highest observed category. That's what we could mean by no measurement error. And likewise, if you are in the highest latent category, you should answer with probability 1 in the highest U category, and therefore probability 0 here. So there's a direct correspondence between the latent and the observed. And that's an interesting model in itself, but it's also a useful trick. Sometimes it could be useful to move observed variables into latent variables, particularly if you want to say, for reasons that you want to make the U and C equivalent, one and the same. And yesterday morning you saw one example of that in the compliance modeling. For those who obtained who were randomized to treatment, they you remember the U variable that was an indicator of C? We know if they complied or not with the treatment. So the U is observed, and in that model, U is identically equal to C for the treatment group. So no measurement error. So that is part of that model. So you can go back and look at it from that point of view. In the version of, we had two versions for that model. One was using an observed U, the other was using training data. Anyway, back to this story then. So how would we represent this measurement error-free situation in Mplus? Well, we want, if you look at the logits here, probability that U equals 1 is what we focus on, traditionally in binary response models. Given C equals 1, that's sitting up there. It should be 0. And how does that translate? Well, we work with our models, we work with parameters that are in the logit scale, not probability scale, although we could do it that way too, but in the logit scale. What's the logit for probability of 0? Well, it's log of the ratio of 0 divided by 1 minus 0. So that's 0 divided by 1. And log of 0 is minus infinity. It's deep down there on the scale. So minus infinity means that that's a logit, minus infinity. That corresponds to a threshold with the opposite sign of plus infinity. And plus infinity can be approximated by 15. 15 gives almost exactly probability of 0. So we're going to see 15 used sometimes 10 used as an approximation for probability of 0. High thresholds, in this case very high 15, correspond to low probability, as we had said yesterday. And in Mplus you say then for class 1 that the threshold for U is fixed at 15. So this 15 here, it gets translated into this statement here. And then let's talk about the other case. For those who are in class 2, what's the probability that they answer U equals 1? We want that to be 1. And that implies that the logit is 1, the probability, divided by 1 minus 1, which is 1 over 0. 1 over 0 is infinity, and log of that is infinity. And therefore the threshold is minus infinity, which is minus 15. So again, a low threshold means that anybody can exceed it, giving a very high probability. So therefore, probability of 1 is a threshold minus 15. So if you want to represent what we have up in this table here, perfect measurement, you use class 1. Number 1 has its threshold fixed at 15. Class 2 has its threshold fixed at minus 15. Now, what if you want to estimate the measurement error? And the interesting thing is that you can identify and estimate a measurement error even when you have only a single indicator, as in the picture on the left. If you have longitudinal data and if you have this kind of regression model where C2 is regressed on C1, you can identify measurement error even with a single indicator. You have the counterpart to that in panel data, longitudinal data, continuous outcomes. This is called an auto-regressive model, A-U-T-O, regressive model. We're going to see a different kind of longitudinal model as we go on. Growth models are growth models, and they are not autoregressive. But for autoregressive model, even with continuous outcomes, is it possible to estimate measurement error? Which is sort of interesting. Usually you need multiple indicators. So here's measurement error then. For those who are in the lowest class, they have a 70% chance of answering that they are in the lowest class, but 30% chance of answering given the wrong answer. This is a measurement error. They are in the low class, but they say that they are in the high category. Likewise, if you are in the high class, you can, by mistake or some other reason, answer that you are in the low category. So the 0.3 and 0.2 are measurement errors of two different kinds. So the measurement error could be of different size for the two alternatives. So how do you deal with that in Mplus? Well, one way of thinking about it is that the probability is 0.3, so the logit will be minus 0.847. You can do these calculations by hand. The threshold is plus 0.847. So you can give that as a starting value if you want to. You don't have to even give a starting value, but that would be a starting value that corresponds to the table up there. And then for the other case, if you start in the high class, or if you are in the high class, what's the probability of answering the high category? Well, it's 0.8, corresponding to that logit value, corresponding to that threshold value, which you give for class 2. So Linda's going to go through an example where you actually find these probabilities, and she's going to devote the example to something relevant for Berlin.
Okay, so we're going to take a look at an example now of latent hidden Markov analysis, and the data that we're going to look at are over here from a German socioeconomic panel data with 5,000 people at 5 time points. And the question is, how satisfied are you on the whole with your life? With 1 being unsatisfied and 2 being satisfied. And we give the reference here down at the bottom of this slide. So I'll leave that over there and just go to the picture here. So here, as I said, we have 5 time points. So we're expanding Banks' example from 2 to 5. And the observed variables are binary, as we said, satisfied, unsatisfied. So we have A, B, C, D, and E as observed variables. The categorical latent variables are CA, CB, CC, CD, and CE. The measurement part of the model are the regressions of the observed variables on the categorical latent variables. So A regressed on CA, B, C, D, E, etc. And this results in thresholds varying across the classes. The structural part of the model is the relationships among the categorical latent variables. So we have CE regressed on CD, CD regressed on CC, CC regressed on CB, and CB regressed on CA. So we have measurement parameters shown here and structural parameters shown here. Oh, whoops, you had already done that. Oh, no. Okay. So on the right screen, we see the Mplus input. So we're familiar with most of this from yesterday. Here's one new option, the freq weight option, frequency weight. So this data, we can have data in Mplus that's response patterns with the number of observations that have each response pattern. And the frequency weight option is used for that. So we're saying that the frequency weight variable, so the number of observations that have each response pattern, is called count. You can see in the used variables list, count is on that list. So all the variables are categorical, they're binary, so we have to use the categorical option to specify that. And the program itself determines how many categories there are, so you don't have to worry about saying that there are 2 categories or 3 or 4. We take that information from the data. And then you can see the classes option. Toward the end of the day yesterday, we saw that we can have more than 1 categorical latent variable. And we use the classes option both to define the variable, give it a name. So we name CA, CB, CC, CD, and CE, and then to say how many classes there are in parentheses. So in our example, each of the categorical latent variables has 2 classes. So that's how you read that input. And then to continue looking at the input, once again, type equals mixture in the analysis command. That's what we've been showing all along. And then we see in the overall part of the model is where we specify the structural part of the model, the structural parameters. So let's start on the second line where we see that we regress CE number 1 on CD number 1. So that's this part of the model, CE on CD. And then once again, you could just say CE on CD without the number 1. We've simplified the language since this input was done. And we just figure out how many there are. And then we have CD on CC right here, CC on CB, and CB on CA, the last one. We also specify the intercepts, CB and CB number 1, CC number 1, CD number 1, and CE number 1. You note that we don't mention CA number 1 because that's an exogenous variable in the model, so the intercept is not estimated as part of the model for that. So now we've sort of looked at the statements, and then let's take a look at the labels that we have. So labels in Mplus can be used to name a parameter, but any parameter that gets the same label is held equal. So what we're saying here is we're basically holding the transition probabilities equal across all of the classes. So we have a 1 following all of the intercepts, which means all of them are going to be constrained to be equal, and they'll all be, so only one value will be estimated, and each intercept will have that value. And likewise, in the multinomial logistic regressions, those regression coefficients are going to be held equal. So all the information from the transition table, like Bengt showed you, the A's and the B's, they're all going to be held equal. So that implies that the transition table is going to be equal across time. And, you know, that sounds to me, anyway, like a fairly restrictive, difficult restriction for fitting the data, because it doesn't seem like that would be probably true in the data across time, that transitions wouldn't necessarily be the same. So we'll see when we look at model fit whether that might have an impact on that. Then, as Bengt mentioned yesterday, when we have several categorical latent variables, we not only have the overall model, but we can have a model for each latent class variable. And so we have that. Let me put this on the other one on the other screen. So we have model CA on the right screen, and then over on the other screen we have model CB, CC, CD, and CE. And as you can see, we have equality labels for the thresholds. And in this model, we're estimating measurement error. And what we're saying with the equalities is that the measurement error is invariant across time. So we're estimating measurement error, and we're saying that it's invariant across time. So we have model CA, CB, CC, CD, and CE. And we have the 3 for class 1 here across time. So the 3 means that those thresholds are held equal across time. And then the 4 means that the same thing for class 2. These thresholds are being held equal across time. And that's saying that measurement error is equal across time. But we're estimating measurement error. We're not doing the first model that Bengt discussed where we fix values at plus or minus 15, saying there's no measurement error. We're doing the second model that he said, which allows for there to be measurement error. So then on this screen, there's nothing new from yesterday. We just have our log likelihood and various information criteria. And you can see the number of free parameters in this model is 5. And then we have a situation where we have our Pearson and likelihood ratio chi-square tests. We talked about them yesterday. And we said, you know, when you have 8 or more binary variables, for example, they're usually not too reliable. But here with 5, you can see that the values of the Pearson and likelihood ratio chi-square are close, and they agree. So when they do agree, then it's safe to interpret them. And what they say basically is the model fits the data very, very poorly. And, you know, this is not surprising given all the restrictions we put on the model, that the transition probabilities are the same across time and that measurement error is the same across time. So this is probably the first situation we've seen where the Pearson and likelihood ratio chi-square actually are interpretable and are helpful in assessing model fit. Okay, and here's additional fit information that we've taken from Tech 10. So just to reiterate what we said yesterday, we have something in the output command called Tech 10, and that's univariate, bivariate, and response pattern residuals, standardized residuals, which will help you assess fit in the parts of the model related to the univariate and bivariate and response patterns when the overall a multi-way frequency table chi-square is not appropriate. But we can take a look here and see what we have. We've got our variables. This is fit for the observed variables to the model. So H0 is our model estimated values. H1 comes from the data. And in the last column, we have our standardized residual. And we're looking for absolute values greater than 1.96. This standardized residual is a z-score. And we can see that everything is very large except for D, for variable D, which it seems to fit the data all right. And my contention is that this misfit comes about because of the latent or the transition probabilities being held equal over time and the measurement error being held equal over time. So we can, but this is, you look at Tech 10 and you can get an idea of what's going on. And clearly, you can see that there's lack of fit pretty much everywhere except for variable D, the fourth time point. Okay, so on this screen, we have information about the observed variables, A, B, C, D, and E. And on the right screen, we have information about the categorical latent variables, CA, CB, CD, CE. And we can compare, I'm going to look at this on the screen rather than jumping back and forth. But if you compare, for example, CA category 1 has a value of 0.44529. And if you look at A category 1, you have the value under the H1 of 0.459. And the difference between those two is it's not measurement error, but it's due to measurement error. And so that's one thing that you can look to see where those values differ. If you go down to CD, the variable that didn't have poor fit, and look and compare that to D, you'll see that they're relatively close. CD is 0.474, whereas D is 0.479. And the category 2 of CD is 0.525, and the other one is 0.521 for D. So the difference between the estimated values for the categorical latent variable and the estimated values for the observed variable are due to the fact that we have measurement error. So now we come to the latent transition probabilities. So here we see how people transition for CA, CB, CC, and CD, and I'm sure CE is on the next slide someplace. But basically, one is unsatisfied. So for people who were unsatisfied at time 1, they were 0.944, or 94% were unsatisfied at time 2, but 6% transitioned into the satisfied category. For those who were satisfied at time 1, 94% remained satisfied, but 6% became unsatisfied. So that's how you read this table. These are the people. This is time 1, and this is time 2. So for class CB, those who were unsatisfied at time 1, these are all held equal because we made that restriction, so it's the same interpretation. So we said by holding our transition tables equal across time that we thought the transition probabilities would remain the same, which may not be the case. But that's basically how you read that. Okay, and then something else that you can look at, we'll leave that there, is we can look at how people agree, or we can look at the measurement error. If we look at these results in the probability scale. So what we have here is a situation where we look at response patterns. And remember, we have 5 observed variables, and there you can either get a 0 or a 1 or a 2, but one of 2 values. So Mplus, if you have the categorical variable, observed variable that's 1 and 2, we turn it into 0 and 1. So when we look here, latent class pattern 1, 1, 1, 1, 1 is people who are satisfied, who say, when they answer their question at each time point, I'm satisfied. Unsatisfied, I'm sorry.
We're looking at the latent class pattern 1, 1, 1. So that's the latent, the true status. And that's the lowest category, goes from 1 to 2.
So
that's unsatisfied. And then for observed variable A, category 1 is the unsatisfied. So 0.841 is the probability that you will answer unsatisfied when you are in the unsatisfied category at time 1.
So you say you're unsatisfied, but you really answer that only 84% of the time. So the measurement error is saying the opposite of what you had actually claimed. So the measurement error here would be 16%.
You have to make note of what's latent and what's observed. And so here, latent class pattern, that's for the latent. So the true status is, at the last time point, the true status is satisfied. They were unsatisfied, 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 satisfied. That's a true status. And then if you look at the measurement error for that, you have it down here. Those who are truly satisfied at the last time point, they have a 84.7% chance of answering satisfied, but 15% chance of answering unsatisfied. So the measurement error is 15.3% here, whereas here it was 15.9. So I think Linda started off thinking that this was the observed, but this is the latent pattern, and this is the observed.
Right.
But anyway, the measurement errors are sitting here in the opposite answer compared to the true status. So about 15-16%.
Okay.
So this takes a little getting used to read these tables, but we just want to experience them with us.
Yeah, exactly. To reiterate, we saw that the model estimated values were different due to the measurement error being different. And then when we look at these results in the probability scale, we see actually what the measurement error is. Here being the 159 and on the other being at the bottom, the smaller value, I think it's 1.154. So these models, I think we have to do some improvements on making them more user-friendly to people. But somehow they've never felt that user-friendly to us. So we haven't gotten quite molded to the point of doing that. So now we look at, model fit information for the latent class indicator model part. Now these are the observed variable response patterns, and this is part of Tech 10. So besides the univariate and bivariate, we give fit information for each response pattern. And at the beginning of the output, we give a number to the response patterns because there are so many of them. So for example, pattern 0, 0, 0, 0, 0, which is all unsatisfied, is 1. And then pattern 2 is satisfied at time 1 and then all unsatisfied. And here's a typo, 33 instead of 3. Pattern 3 is 0, 1, so unsatisfied, satisfied, unsatisfied, unsatisfied, unsatisfied. So you get the idea. And here's pattern 32. So because we have so many, we give them each a number. And then, actually I should put this on the other screen. And then you can, using the number here, the response pattern number, then you can look at the standardized residuals that are large and see them which response pattern that's from. You can also look at the contribution that response pattern, the individuals that have that response pattern make to the Pearson chi-square and to the log likelihood. And basically all all of these values will be large for the same response pattern, but they're just different ways of looking at it. So, for example, here's one response pattern that's fairly large. For number 16, they have a standardized residual of 5.44. They make a contribution to Pearson chi-square 28.08 and to the log likelihood minus 138.07. So let's see who are the people in pattern 16, or what is that response pattern? And if you come over here, you can see that they were people who were satisfied for 4 time points and then at the last time point became unsatisfied. So that's how you look at that. And then you can find which response patterns have the largest standardized residuals and contribute most to the misfit of the model. You can do this with categorical outcomes. And it may be an issue in people answering incorrectly, or reliability of the measure, how the measure is being asked, whatever. But it may point to you investigating how you're collecting the data and why somebody would make some sort of a transition that doesn't really fit the full model. But basically, we have to also remember that this model did not fit the data well based on both the 2 chi-squares and also Tech 10. So this is the latent hidden Markov model. Very restrictive, with the measurement error and latent transition probabilities being held equal over the time points. Now, if you're interested in having additional information about these, then we have these 2 references that you can take a look at. So do you have any other comments on this?
Yes, I'm tempted to say a couple of other things about it that I just thought of when I was sitting there, which might be of general interest. If you take a look at slide 16, so Linda pointed out that the modeling here used 2 critical assumptions that may not hold. One was time invariant measurement error, and the other was the same transition probabilities for all time points, and neither one of which may hold. There is another restriction in this model, which, and I should say, you can probably relax the assumption of time invariance of the transition probabilities, so they can be different at the different time points. I don't know how far you can go in relaxing the invariance of measurement error across time, because with a single indicator, the measurement error identifiability, I think, hinges on at least a couple of time points being equal. So you're sort of caught in a difficult spot there. You have to make an assumption that may not be true just to identify the model. But then there's yet another thing that we should think about. These are called Markov models, and it's actually called a first order Markov model. First order autoregressive model. First order meaning that CA influences CC and CDCE only indirectly through CB. That is, CA does not have a direct arrow to CC, does not have a direct arrow to CD, or a direct arrow to CE. So it's this simple chain that is the hallmark of a first-order autoregressive model. And it's not necessary to have that restriction. You can say in Mplus, you can say CC on CB and CA. So CC on CB, CA, that means that you add a direct effect here. And that may fit better also. And in fact, Mplus allows this generality. You can have all of the CE can be related to all of the previous variables. And in fact, the reason this autoregressive model is so popular is because it's simple to compute. So when you have very, very long time series, like 100 time series, in statistics, there is a particular simplification to the algorithm if you only allow for first-order autoregressive. Mplus has not yet built in that simplification. So when you have many time points and many indicators, Mplus is heavy, but it's very general on the other hand. So Mplus for latent transition analysis today is more suited to shorter series, like 2, 3, or 4 time points. Well, this didn't take a lot of time either, so just an aside. So then we move from the hidden Markov model to the close cousin of latent transition analysis, and we show the difference by having fewer time points, which is typical, and having more than one indicator per time point. So we have here 4 indicators per time point, and it's the same 4 indicators at each of the 2 time points. And now we're still interested in the transition from C1 to C2. So we're interested in the same kind of transition table, but we also expand the model, which is typically done as a model which regresses C2 not only on C1 but also on X. So some kind of covariate here, say gender, which will affect the intercept of C2 and which will also affect the intercept of C1. So gender will affect the class probabilities at the 2 time points. So the idea then being that the standard setting for latent transition analysis is that you have longitudinal data. I guess you should cross out cross-sectional data. So we have a correction on both page 27 and 32, Linda. And multiple items measuring several different constructs and hypothesized simple structure for measurements, and the construct represented as a latent class variable. And the aim is to identify items that indicate the class as well. And you recognize that from latent class analysis. At each time point, we are going to focus on the latent class model that we talked about yesterday. So everything you heard yesterday afternoon will be relevant here. And we want to study the relationship between the latent class variables, that's transition probabilities, estimate class probabilities, relate class probabilities to covariates, and ultimately do the what I call the factor scoring step, the classifying of individuals into classes by their posterior probabilities. So that's the setting, and it is really then drawing quite a lot on what we already know, so illustrating the fact that as we go further in the course, it doesn't get more complicated, it gets more easy and perhaps more interesting. So I think at that point, Linda will give you an example.
Okay, so in this example, the difference is that we have as Bengt I think mentioned already, the multiple indicators at each time point, which would make the identification of measurement error differing across time easier than in the first example where we only had one indicator at each time point. And so here we have the 4 indicators, U1 at time 1, at time 2, 3, 4, U2 at time 1, 2, 3, 4, C1 and C2. So the relationships here, the C1, you recognize this from yesterday, a latent class analysis. C2, a latent class analysis here. These are the measurement parameters, and the structural parameters are shown in C2 on C1. And then we've added a covariate, so we can regress C1 on X, and C2 is regressed on C1 and also on X. So we've expanded the model in 2 ways. 1, we have multiple indicators, and 2, we have covariates, or 1 covariate, but a covariate. Okay, so the input, nothing new. Here's our classes option where we name C1 and C2. They have 2 classes each. And in the overall part of the model command, we show the structural part of the model. We regress C2 on C1 and X, and we regress, so that's C2 on C1 and X, and then C1 on X, right there. So this is the structural part of the model. This is where we obtain the intercepts and the logits that we use to create the transition table. So at the very early in the day here, Banks showed you a table that has a lot of A's and B's in them, and those A's and B's come from the intercepts and regression coefficients in the structural part of the model. Now, Mplus gives you that transition table, but if you want to make adjustments to it, then you would have to understand what those are. But that's described not only on the slide earlier in the day, but also in more detail in Chapter 13 of the User's Guide. Now, the next part of the output describes the measurement invariance across time. So in this example, we only have 2 time points, so there's only one latent transition table because we only go from 1 to 2. We don't have a third time point going from 2 to 3. So the equality of that transition table isn't an issue in this situation when we have 1. We can have measurement invariance across time that is shown in the model for categorical latent variables C1 and C2, where the variables at time 1, so U11 through U14, so these variables are held equal across time by the 1-4 in parentheses. So then 2, 1, 1, 2, etc. Like that. And then likewise measurement invariance here, where we show the 5 through 8 label. So with the labeling in Mplus, if you have a list of variables like we have here, U11 -U14, you can have a list of labels, 1-4. So U11 $1 will get the label of 1, $2 will get the label of 2, $3 gets the label of 3, and $4 gets the label of 4. So these 2 equalities are holding the measurement invariant across time. So I'll just put the general test, So here's our tests of model fit that we normally get that are used mainly the log likelihood in comparing nested models. The BIC can be used to compare models. But we also get our other fit statistics, and here's the Pearson and likelihood ratio chi-squares. And once again, we have 4 variables at each time point. And if we look here, it looks like the Pearson and the likelihood ratio chi-square agree, and they, based on the p-values, they say that the model does fit the data. So we're not able to reject our null hypothesis. So the model does fit the data based on those tests. Okay, and then we have our model results. Let's first look again at the bottom here. So the classes are represented by time and class. So class 1 is class 1 at time 1 and class 1 at time 2. And class 2 is class 1 at time 1 and class 2 at time 2. So let me just say, are you going to write it? So 1, 1, 1, 2, 2, 1, and 2, 2. Thank you.
Apologies for the handwriting.
Well, how did you do that without making it go forward?
Turn it up.
Oh, left-handed, I guess. Could you make that go away because it's in the front of what you just wrote? I guess we should just be non-technical, just like we've always been, not try something new. But anyway, so these are class numbers. Class 1, class 1, class 1, class 2, class 2, class 1, class 2, class 2. And this is time, 1 and 2. So class 1 at time 1 and class 1 at time 2, etc. So the reason I'm telling you this is because when you look, now we're going to look at thresholds on the other screen. I don't want to touch that one. Okay, so, well, it's hard to look at them all without now moving that one. But anyway, we've held certain things equal. And so when we look at the results for class 1, it's going to have class 1 at time 1, class 1 at time 2. And we should, everywhere we have ones, the threshold should be held equal. So 1, 1, 1, 1. So if you look at your results, you should see in class 2, the first part, first of all, in class 1, everything should be equal. And you can see that it is. If you look at the first four, 2.020, 2.003, 1.776, 1.861, and that's equal to that. And if you go to class 2, then the first four numbers are going to be the same because that's all class 1. But then this will be different, but it's going to be the same as everything else that's 2 here. So we're looking at the 2 there. If you go to class 3, the first part should have those numbers, and the second part should have the numbers from 1. And then if you go to class 2, or rather to class 4, both of these will be equal. So just to show you how those equalities that we set come about.
So just to add to that, you may want to draw a line here in your output, to distinguish between time point 1 and time point 2.
Right.
And then you can maybe more easily see what's going on.
So here we have 1, 2, which is, you took that away. Well, anyway, so basically, if you wrote down the little numbers that Bengt wrote down, the 1, 1, 1, 2, 2, 1, 2, 2, then you should be able to go through the 4 sections of the output for class 1, time 1, class 2, time 2, so 1, 2, and see how those equalities come about. So one group is going to have thresholds that start out negative 2.020, and the other group 1.964. So that, and those equalities represent the measurement invariance being equal across time. And then if we leave the measurement part of the output and go on to the structural part, once again, just like we saw in the other example, here are the structural coefficients, and you can use these, although we do give you the transition table in the output. These are the values, these logits are the values that are the A's and B's in the transition table that Bengt showed you at the very beginning of the day when we discussed this. So C2 on C1, C2 on X, well, these wouldn't be part of the transition table, the covariates. Are they? They are. Okay, so these give you the coefficients, and these are the A's here. The intercepts are the A's, and the regression coefficients are the B's. And then you can create that transition table, modify it, or use the one that we give you. And once again, that's gone over quite a lot in Chapter 13. Now, one of Bengt's students, Karen Nyland, former students, did her dissertation on latent transition analysis and came up with a strategy to do this type of analysis. And basically, to study the measurement model at each time point is the first step. So we had 2 time points, and as I mentioned, each time point was really a latent class analysis. So as a first step, when you're doing any type of latent transition modeling, you should start out with a latent class analysis at each time point. That's a good way to get an idea of what's going on. And one thing that you might be looking for is if you actually have the same number of classes at each time point. So let's say at time point 1, the best fitting model is 4 classes, and at time point 2, it's 3 classes. So you can learn information by doing that. And then you can explore the transitions based on the results. So you might, to get an inkling of how people transition from one time point to another, you can use your information on most likely class membership and create crosstabs where you can see how people transition from one class to the other. So you would have the most likely class membership variable for each categorical latent variable, and you could do a crosstab of those two and actually see then where people move from between the 2 time points. And that can give you an idea of what your model will look like when you finally put everything together to estimate it. Karen recommends exploring the latent transition model without covariates as a first step. And as Bengt mentioned yesterday, we've gone back and forth on whether one should estimate these models with or without covariates, and I think our thinking today is that we would estimate them without covariates, and if we then add covariates and that dramatically changes how the classes look, then we would be suspicious that there might be a need for direct effects in that model. And then you can test for measurement invariance across time. So we show in both of the models that we looked at, we specified measurement invariance across time. But one can actually test that, whether that holds or not, by doing the same thing you do when you're testing for measurement invariance in structural equation modeling in a multiple group analysis. Only in this situation, it's across time. You can test a model that has equalities across time versus a model that doesn't have equalities across time to see whether the measurement invariance holds. And then including your covariates in the model. And then once you've done that and once you've gotten to a solid place, you can also go on by including distal outcomes. And we'll be talking about models with distal outcomes today. So your classes can be predicting something beyond the time of the longitudinal analysis that you're looking at. And you can also add other modeling extensions. For example, a latent transition model maybe can be part of a larger model that contains another type of growth model or another regression model. So, and the source for these suggestions is Nyland 2007, which is available on our website, and it can be downloaded. And it actually looks like we should take questions. Do you think?
And just to add to that, the Nyland dissertation then goes through the details of how to calculate transition probabilities when you have covariates like male-female dummy X variable. So she has all the details in that dissertation. So that might be useful for you to take a look at. And those steps, I think, are really helpful. So step 2 there, you do a latent class analysis at each time point and classify people, and then you get the crosstabs, and it's very down to earth, and you can look at it before you go into the longitudinal modeling.
And you save that most likely class membership for the people who weren't here yesterday by using the save data command, save equals C probabilities.
So now we have a 15-minute time period for questions and answers, and we have a microphone being passed around because this is being videotaped. So who's going to be the first brave person? You're getting braver and braver.
Yes, probably I'll be bravest on Tuesday then. But yes. If we can go to slide 41.
41?
Slide 41.
Yeah. So I'd just like to ask, you've got the estimates and the standard error. Why haven't we got confidence intervals? is that easy to output from Mplus?
If you want confidence intervals, you use a special output command called cinterval.
Okay.
And I think we give that here, right?
Yeah.
Right.
Okay.
So then you would get, there's 3 different types of confidence intervals that you can request.
Excellent. Okay, thanks.
You're welcome.
In front.
I have some questions about the output. Going to slide 22 compared to 23.
Okay, I'll do 22 if you do 23. Okay.
Now, in 23, that's the one, that's the one on the left. H0, that's the model probabilities. And then on the next slide, it's also, it shouldn't it be the same, 0, 44, 5, 2, 9. Should this
So
be the same as the one at the former slide, or what?
This?
The difference between those two?
Are you looking at this on the left?
Yes, that on the left, shouldn't that be the same as that on the right?
Do you want to answer that?
Well, one is for the observed variables,
Yeah.
A, and this is for the estimated for the categorical latent variable. So basically, because we've allowed for not to have or to have measurement error, we have a model where we're allowing measurement error. So we wouldn't necessarily think the model estimated values for the observed variable would be the same as the model estimated value for the categorical latent variable.
Oh, I see.
That would only happen if we didn't allow measurement error.
I see. I have another slide. That's 25.
35?
25?
25.
25? Okay.
Yeah, 25.
Are you saying 25?
Yes, that one. The 2 last column. What's that for numbers?
Which one?
The
Slide
0, 8.
25. What's your question?
The 2 last columns. Which what's that? These 2. Yes.
So the first column is always the estimate.
Yes.
Oh, yeah. So and the second column is standard error.
That's the same pattern. That's the
Standard
same
error.
pattern.
Sorry, we probably
Yes,
should
yes.
have the heading. Sometimes we
ratio.
can't fit everything on the
Okay.
slide. So whenever you see 3 columns, it's usually parameter estimate, standard error, and ratio of the 2.
Sure. Okay. Thank you.
Good. It's good to get the basics cleared up so we can focus on the exciting stuff. More questions. You don't get coffee yet, folks. Oh, one more question. You can squeeze it out. Something you really elementary thing we want to hear now. Yes. Oh, right.
Brave soul.
It's maybe quite technical. You're referring a couple of times to models, Markov models, which are strong in the time dimension. Do I really understand that if you design such a model, you really have to replicate for each time period the complete model? Because if you have a model with 100 time points, the model then extends also to 100?
So you have a model that is longitudinal, but you want to extend it in which way?
If you have a model which have about 100 time points.
100 time points?
Yes. And maybe small in the panel dimension, but strong.
So few measurements and a long time series. So
Yes,
the standard Markov setting in statistics. How would that? Are you asking how that would be handled in Mplus?
Yeah, in the specification of your model, because I understand you really need to specify each time period separately.
Right.
Okay, so you get a long repetition of all these.
Right.
Time.
So as I alluded to, I think.
Can't you use the list function in on? I mean,
But I think he's asking about how does Mplus handle a model with 100 time points, say?
but you're asking how you specify it, right? Like Z on Y, Y on X?
You have to say C2 on C1, C3 on C2, C4 on C3, C100 on C99.
Okay.
But you shouldn't do that because, as I alluded to, Mplus right now is not set up algorithmically to handle very long time series. You couldn't do 100. It would be just too cumbersome. because we don't utilize that simplifying algorithm of equal transition probabilities, which simplifies the algorithm. So it's Mplus right now, like transition analysis, is more suited to short time periods, no more than
general.
5, I would say.
And it's more general.
But it is more general. You don't have to assume the first order or order regressive. So the issue doesn't really come up. But we're planning to expand it to do those long time series too. We were too excited about other things right now. So.
A not very exciting question, but on slide 34 and 35, the input.
Okay.
I'll do 34.
I'll do 35.
The model command.
34 and 35.
Yeah. I think you said something about that yesterday, but you're saying here C2 on C1, and you have this number 1 sign. That's not necessary, or what does it mean again? Do you have to put it there?
If you had a situation where you had 4 classes, and then you were specifying a multinomial logistic regression, C4 would be the reference class, so you'd have to say C number 1, C number 2, and C number 3 on C number 1, for example. But you could instead just say C1 on, or C2 on C1. So wait, I didn't say that quite right. So you would have to, if you had 4 classes instead of 2 classes like we have now, you would have to say C2 number 3, C2 number 2, and C2 number 1 on C1 number 1. The shorthand for that would be C2 on C1. So you used to have to specify each of the classes except the reference class using the number sign, but now you don't have to do that. Now if you say C2 on C1, we know how many classes there are of C2, and we know how many classes there are of C1. So we just create behind the scenes all of the on statements that you would need. But we allow you to not specify them all by having the number 1 option available.
And another angle to that is, just remember the multinomial logistic regression. There is 1 regression coefficient for each of the response categories, except the last. This language, where you explicitly say which number it is, makes it possible to refer to a specific parameter, whereas Linda's shorthand refers to all of them. But sometimes you don't want all of them. You want to get in and look at each little parameter, and that's what that is.
But in the output, it will show you each parameter with the proper label, so you'll know which is which.
I think we had one more question further back.
I have a question related to page 33.
33?
33?
Oh, sorry, and the coefficients on 33. So if you take that one, and when we look the coefficients from page 41. So I was just wondering how
wait a second. You're talking about pages 33 and 41? Is that right?
41, yes.
So 33 and 41.
Okay.
So I was just curious and checking how you interpret these coefficients from C1 to C2, which I think is 0.53.
Okay, so so C2 number 1 on C number 1 has a logit estimate of 0.530. Is that right? Yeah. Okay.
And what's the question? How do you interpret that, is the question. Okay. Well, first of all, I think you could do it at different levels of ambition. First of all, you note that it is positive and significant. So that means that the higher, that if C1 is in first category, you're more likely to have C2 in the same category. Otherwise, it would be a negative sign. But really, the easiest interpretation is when you turn these coefficients into the transition probabilities, which is given in the output. So bringing it down to the probabilities is probably the easiest way to do it, like looking at it this way. That's part of the output. But you can certainly look at the sign of these so you can see which direction it goes into. Okay, are we ready for a 20-minute coffee break? I think you've disturbed it. All right. Thank you.